For millennia, humanity has gazed at the sun, our life-giving star. Yet much of it remained unseen. Despite centuries of study, the sun's poles were a complete mystery, hidden from our view. Imagine trying to understand Earth without ever seeing the Arctic or Antarctica. That's how little we knew about our own star. But now, for the first time, we've captured direct images of the sun's south pole. And what we're seeing is transforming our understanding of the solar system. This achievement is as monumental as seeing the far side of the moon for the first time. Our vantage point has always been limited to the sun's equator, since all planets, including Earth, orbit in a flat plane. To see the poles, we needed a spacecraft to break free from this plane, a feat requiring years of planning and engineering. The result: a perspective no human or telescope has ever had. The sun's poles are the birthplace of its magnetic field, and the solar wind that shapes our entire solar system. Unlocking their secrets is key to understanding solar storms, space weather, and the very nature of stars. With these new images, we're opening a new chapter in our relationship with the sun. Why did it take so long to see the sun's poles? The answer lies in the architecture of our solar system. Picture the solar system as a spinning record, the sun at the center, planets orbiting on a flat plane called the ecliptic. From this vantage, we always see the sun's equator, never its top or bottom. To glimpse the poles, a spacecraft must leave the ecliptic, a maneuver that demands immense energy and precision. Changing a spacecraft's orbital tilt is one of the hardest challenges in spaceflight. For decades, this made direct polar observation impossible. The poles aren't just a curiosity, they're the engine room of the sun's magnetic field. Magnetic field lines emerge from one pole, loop through space, and re-enter at the other, driving the solar wind. Previous missions like Ulysses flew over the poles, but couldn't take images, only measurements. It was like hearing about a masterpiece without ever seeing it. We knew the poles were crucial, but we needed to see them to truly understand the sun. Only with new technology and daring trajectories could we finally capture these elusive views. Now, for the first time, we can study the sun's poles directly. This breakthrough is reshaping solar science. Enter Solar Orbiter, a joint mission by ESA and NASA, built to reveal the sun's poles. This spacecraft is a solar laboratory, equipped with 10 instruments to study magnetic fields, solar wind, and energetic particles. To survive the sun's heat, it's shielded by layers of titanium and a special heat-radiating coating. Its instruments remain cool, even as the exterior faces temperatures over 500 degrees Celsius. The real genius is in its path. Solar Orbiter uses gravity assist from Earth and Venus to tilt its orbit, gradually rising above the ecliptic. After years of careful maneuvers, it's finally giving us our first direct images of the sun's south pole. Some instruments observe the sun, while others sample the environment around the spacecraft. This lets scientists link solar eruptions to the solar wind in real time. For the first time, we can connect what happens on the sun's surface to what sweeps through space. Solar Orbiter's coordinated approach is revolutionizing our understanding of the sun. Its journey marks a new era in space exploration. What do the first images of the sun's south pole reveal? A landscape of swirling plasma and magnetic chaos. Unlike the large sunspots near the equator, the pole is covered in countless small bright features, footprints of magnetic loops. These loops shift constantly, creating a dynamic, ever-changing texture. The sun's magnetic field behaves differently here. At the poles, field lines open outward, forming coronal holes, the source of the high-speed solar wind. Watching these regions evolve in real time is giving us unprecedented insight into how the solar wind is generated. We also see mysterious features like solar moss, delicate patterns of superheated plasma, and spicules, jets of material shooting up at incredible speeds. These small-scale events may help explain why the sun's outer atmosphere, the corona, is millions of degrees hotter than its surface. The pole is a turbulent living system, the engine room of the solar system in action. Every flicker and swirl contains clues to the sun's fundamental processes. By studying this new landscape, we're learning the language of our star, written in plasma and magnetism. These discoveries will keep scientists busy for years to come. The sun's poles are more complex and dynamic than we ever imagined. We're finally beginning to understand what they're telling us. The sun isn't constant. It pulses with an 11-year cycle, driven by its magnetic field. During solar minimum, the sun is calm. At solar maximum, it erupts with sunspots and flares. The key to this cycle lies at the poles, where the sun's magnetic field reverses. Over each cycle, the magnetic north and south poles swap places, a process that starts at the poles and ripples across the sun. By observing the poles directly, we can watch this magnetic reversal unfold in real time. We see old magnetic fields swept away, and new ones emerge, like a cosmic tide. These observations let us test and refine our models of the sun's internal dynamo. The strength of the polar fields at solar minimum helps predict the next cycle's intensity. Accurate polar measurements improve our forecasts for space weather. This is vital for preparing for solar storms that can impact Earth. Understanding the sun's cycle isn't just academic, it's practical. It's the difference between being caught off guard and being ready for the next solar storm. Solar Orbiter's data is transforming our ability to predict the sun's behavior. The sun sustains life, but it also threatens our technology. Solar eruptions can unleash storms that disrupt power grids, satellites, and communications on Earth. The 1859 Carrington event caused telegraph failures and auroras as far south as Cuba. Today, such a storm could cause trillions in damage. Our interconnected world is vulnerable to space weather. Solar Orbiter's mission is crucial. By understanding the sun's poles, we can better forecast dangerous solar events. Improved models could give us days of warning instead of hours. This extra time lets us protect power grids, satellites, and flights. Studying the sun is planetary defense. Just as we track asteroids, we must monitor our star. The sun is the greatest natural hazard to our technology. Knowledge from the poles isn't just curiosity, it's a tool for survival. Solar science is an investment in our future. By understanding the sun, we safeguard our civilization. The stakes couldn't be higher. These first images of the sun's south pole are just the beginning. Solar Orbiter's orbit will become even more inclined, offering clearer views of the poles in the coming years. By 2029, it will capture the most detailed polar images ever. We'll witness a full magnetic reversal unfold, a cosmic event never seen before. Solar Orbiter is part of a fleet. Parker Solar Probe samples the corona up close, while ground-based telescopes provide detailed surface views. Together, these missions are building a complete 3D picture of our star. The sun is the only star we can study in such detail. What we learn here applies to stars across the universe. Understanding our sun helps us grasp the workings of countless other stars. This exploration puts our solar system in a grander cosmic context. Looking at the sun in new ways changes how we see ourselves, fragile, curious, and capable of great discovery. It's a lesson in humility and inspiration. Seeing the sun's hidden face connects us to our past and secures our future. The sun has revealed a new face and illuminated our path forward. Thank you for watching. If you enjoyed this video, please like and subscribe for more. And remember, keep asking, keep exploring. The answers are infinite.